Today we'll be looking at how neutrons' evil twins may be crushing stars into black holes. If you're new to this channel, welcome. This is Mr. Singularity, where we explore the scientific and technological breakthroughs shaping the future as we know it. The cosmos could be packed with mirror particles, and these otherwise undetectable particles may shrink the densest stars in the universe, making them into black holes, recent research indicates. These imaginary evil twins of ordinary particles would undergo an inverted version of the laws of physics, as if the rules governing known particles were mirrored in the glass they stared at. According to a recent report released in December 2020 in the arXiv preprint archive, but not yet peer-reviewed, if these particles occur, the densest stars in the universe will shrink into black holes. Several basic symmetries in existence give rise to the laws of physics. The opportunity to transfer experiments or interactions in space and have the same result contributes to the retention of momentum. But one of these symmetries, the symmetry of reflection, is not necessarily obeyed. The symmetry of reflection is when you look at the mirror image of a physical reaction. You get the very same outcome in nearly all situations. For example, if you throw a ball in the air and catch it, it appears just the same in the mirror. Gravity respects the symmetry of reflection. Yet, not all the powers are playing together. The violator of reflex symmetry, also known as mirror symmetry, p-symmetry, or parity, is feeble nuclear power. If a weak force is involved with any particle interaction, the mirror image of the interaction can appear different. The classic experiment that first observed this effect showed that as radioactive versions of the cobalt decays, the electron it releases tends to travel in one direction, in particular opposite the direction of the cobalt spin, rather than in any random direction. If the weak nuclear force obeyed the symmetry of reflection, so those electrons could not know which way is which, and they would pop out however they pleased. Physicists have no idea whether the symmetry of the mirror is disrupted in our world, but others have offered a radical explanation. Maybe it's not broken at all, and maybe we're just looking at the universe the wrong way. You can rescue the mirror symmetry if you allow any extra particles to remain. And by some, I mean a lot. A mirror image replica of any single atom. There will be reflection electrons, mirror neutrons, mirror protons, Z-Boson mirrors. If it's got a mirror, you call it. This is distinct from antimatter, which is like natural matter but has an opposite electrical charge. One of the terms for mirrors includes shadow matter and Alice matter, as in through the looking glass. By adding mirror matter, reflection is retained in the universe. Ordinary matter performs left-hand interactions, and mirror matter performs right-handed interactions. All are synchronized at the statistical level. The star's heart. But how are scientists going to test this radical idea? Since the only force breaching the mirror symmetry is a weak nuclear force, it is the only force that can have a channel to interact with its mirror counterparts on a regular basis. And the weak force is really weak because though the universe was filled with mirror particles, they could hardly be observed. Many studies have concentrated on nuclear particles such as neutrons, so they do not have electric interactions, making experiments simpler. Seeking for mirror neutrons hasn't come up yet, but all hope isn't lost. This is because these studies have taken place on Earth, which does not have a super strong gravitational field. But theoretical physicists expect that a very strong gravitational field will strengthen the relationship between neutrons and mirror neutrons. Fortunately, evolution has already invented a much better scientific device to search for mirror matter: neutron stars. The neutron stars are the remains of giant stars. They are incredibly dense. A single teaspoon of neutron star material will overtake the Great Pyramids, and extremely tiny. Imagine cramming 10 suns worth of content into a space no greater than Manhattan. Neutron stars are basically city-sized atomic nuclei consisting of individual neutrons packed together as closely as possible. The evil twins of neutrons. With an enormous number of neutrons combined with the intense gravitational field, the tallest mountains on neutron stars are only a half-inch high. Strange things are likely to happen. All of those things, the new research indicates, is that neutrons often transform into their mirror neutron equivalents. A few things happen when a neutron transforms into a mirror neutron. The mirror neutron still hangs within the star, it's gravitationally bound, so it can't go anywhere, and the mirror neuron has its own tiny gravitational power, such that the star does not evaporate. Yet mirror neutrons do not partake in the interactions that scientists observe in neutron stars, thus altering internal chemistry. They do take part in a mirror neutron star life, with its own series of interesting atomic interactions. But life is concealed from us, like a ghost inhabiting the body of a normal neutron star. It's like going to a packed soccer game and slowly replacing spectators with cartoon cutouts. The arena is still full, but the excitement is gone. As neutrons slowly transform into mirror neutrons, the star is diminishing. At a 1-to-1 ratio of normal neutrons to mirror neutrons, the neutron star is nearly 30% smaller. Neutron stars can survive the crippling weight of their own gravity by a quantum mechanical mechanism called degeneracy strain, but the strain has a limit, and with less normal neutrons, the limit is shrinking. If the star had a 1-to-1 ratio of regular neutrons to mirror neutrons, the overall mass of neutron stars in the universe would be around 30% less massive than we would usually anticipate. More massive than this, the neutron stars will crash into black holes. Scientists have seen neutron stars greater than this, which may at first sight suggest that mirror matter is a dead-end notion, and we have to find some other explanation for mirror symmetry violation. But the case is not closed. The universe is just too old, 13.8 billion years, and we have no idea how long this phase of transition will take. It's conceivable that there simply wasn't enough time for neutron stars to make a switch. The cool thing about neutron stars is that astronomers look at them all the time. Through discovering and studying more neutron stars, they may only see a sign in some of those signals that there is a secret mirror, and I dare say evil, the field of the universe. What's your take on this? Let me know down in the comments below and check out one of these other videos. This has been Mr. Singularity, and I'll see you on the next one.